Example 9. Analyzing a discontinuous derivative. So in the previous example, we looked at a derivative that was continuous and graphing f of x based off of that derivative. Now we're going to look at a graph where the derivative is discontinuous and where we need to come up with a continuous function where a derivative is discontinuous. Remember, you can have a continuous function and the derivative be discontinuous. That just means that we have a cusp or a corner or something like that. So take a second, pause the video, and make sure you graph this derivative accurately on your paper. Okay, so we're given a function that is continuous on the interval -4 to 4, and that's shown right here. We want to find the x-coordinates of all the extreme and inflection points, and then sketch the graph. The x-coordinates of the extrema. So we will have an x-coordinate at an extrema where certain things happen. So let's talk about what those things are. The x-coordinates we also know as the critical points. The critical points happen where f prime of x equals 0 or where f prime of x does not exist. It's important that we label both of them. So let's look at our graph right here. We have that the x-coordinate of this derivative is 0 here, here, and here. So we have that f prime of x equals 0 right here, and right here. So x equals -3, x equals -1, and x equals 1. We also have that the derivative does not exist right here at 0 because it's discontinuous, and right here at 2 because it's discontinuous. So we get the x-coordinates are as follows. -3, -1, 0, 1, and 2. We have that the x-coordinates are either 0 or does not exist at these points. So now what we're going to do is we're going to use the first derivative test in order to determine max or mins. So the first derivative test involves a sign chart. And we're going to just plot all of our x values. So -3, -1, 0, 1, and 2. Now because this is on a closed interval, we need to make sure that we include the endpoints, -4 and 4. If it was from -infinity to infinity, we would still include those, but we don't necessarily need to mark those on our graph or on our sign chart. Okay, so we don't actually have to plug anything in. In fact, we have nothing to plug into. However, we can determine all of these. So we need to see between -4 and -3. Between -4 and -3, right here, our derivative is positive. Then from -3 to -1, our derivative is negative. Then from -1 to 2 or to 0, it's positive. So here we have that it's positive, negative, positive. Now try to see if you can fill in the rest on your own. Okay, so let's go back to the graph. Between 0 and 1, we have that the graph is negative, the derivative, and here we have the derivative is positive, and here we have the derivative is negative. So negative, positive, negative. Now in another color, I'm going to signify what the actual graph is doing, what f of x is doing. F of x is going up, f of x is going down, f of x is going up, f of x is going down. Increasing, decreasing. This is going to help us graph. So in words, we're going to write this. A local max where f of x goes from where the derivative is positive to where the derivative is negative is a local max by definition. This happens at certain x coordinates. This happens at x equals -3, 0, and 2. A local min is where the derivative goes from negative to positive. This happens at these x values, -1 and 1. Make sure you understand this, that at -3, or from -4 to -3, it's increasing. Then at -3 to -1, it decreases. So at -3, it changes from positive to negative. Then at -1, it goes from negative to positive. So we have a min. Here we have a max, here we have a min, here we have a max, here we have a something. Now we need to look at the endpoints. This is very important to also look at the endpoints, because it's going to tell us how to start our graph. So at the endpoints, we have a local min at x equals -4. Since x equals -4 is a left endpoint, and the derivative is positive as we head away from -4. So when x is larger than -4. Then we have a local max at x equals 4. Since x equals 4 is a right endpoint, and the derivative is negative as we go away from 4, so when x is less than 4. Okay, so that gives us our local mins and local maxes. It's easy to see it in the sign chart as well, because here this -4 is smaller, and here this 4 is also smaller. Okay, inflection points. An inflection point happens when the second derivative changes sign. So when the derivative goes from increasing to decreasing, or decreasing to increasing. So let's look at where this happens. Well, here the derivative doesn't change sign. It's always increasing. Here it's constant. Here is the only place where something funny happens. Here the derivative is going down. It's decreasing. And then here it starts increasing. So we have an inflection point right here at x equals -2. So at x equals -2. Now we have all of our pieces. Now for the fun part, we get to graph. Okay. Again, we're making our graphs nice and big. No shame in making big graphs. So we got to pick a starting point. Why not start with an endpoint? So I'm going to put my endpoint right here. If you want, you can also put it down here, up here, anywhere. Here, it doesn't matter. I'm going to put mine right there. Now I know there's a max at -3. So I'm going to put it somewhere like up here. I know that I have an inflection point at -2. So I'm just going to put a dot at the inflection point. I'll do that in a different color. My inflection point, we'll say about there. It's going to be my inflection point. And I know I have a min at -1. So I'm going to put a dot right there. I know at 0, I'm going to have another max. So I'm going to put that right here. I know that at 1, I'm going to have another min. So I'm going to put that right there. And then I know at 2, I'm going to have another max. So I'm going to put that right, we'll put it about there. Now this looks pretty crazy. So right here, I'm just going to label these. This is a max. This is a min. This is an inflection. This is a min. This is a max. This is a min. and this is a max. Here we go. Let's attempt to draw this. Now, I'm concave down from -4 to -2 because if we go back up here, the derivative is decreasing. So I'm concave down from here to here. I'm concave up from here to here because the derivative is increasing. So I need to be, and again, I don't have an art degree, so bear with me. Concave down, hit the max, concave down, and at -2, I inflect. I twist. To be concave up, I hit the min, and I go back. Still concave up. Now something funny happens. At 0, if we recall at 0, our graph does not exist, which means there's a cusp or a sharp point. Okay, so I'll make that cusp like this. It goes up, and then it goes down like this. This is a min. And then I got to go up to my max. No inflection point, so I stay concave down. Oops. Get a little more curve in there. And right here, there is another discontinuity, so I know it's going to be sharp. And I know actually the slope is -2, so I'm going to go down 2 over 1, I'm going to do my best, like this, all the way down to 4, where I will get my final ending point right there. And that's how you make a possible graph for f of x. So this is a f of x possible graph. And it's beautiful.